Lesson 4.3, now we're talking about rotations. And again, you covered some of this in middle school classes, but probably not all of it. So rotation is a transformation, but this time you're spinning it. It's being spun around a fixed point, and that point is called the center of rotation. So if you could draw rays from the center of rotation to the point in the image, that gives the angle of rotation. It's like down here, you see this little black part there coming out of P. That's your angle of rotation. And those lines not actually on your shape. Your shape there is QR. Looks like a flag kind of thing. So the lines there for the angle of rotation is something you add in yourself. It's not normally there. So the thing with rotations is that sometimes they're counterclockwise, sometimes they're clockwise. So you have to know which direction you're going because it does matter. This one was a counterclockwise rotation. Some geometry textbooks say all rotations in this book are counterclockwise. Some say all are clockwise. Yours does both, I think. So there's different ways to do rotations. With this one, if they give you an angle that's not like 90, 180, 270, something like that, you can use a protractor. So here you have triangle ABC, and they want to rotate this around point P. You want to go 120 degrees. Very easy to do. First, you draw a line segment going from P to A. And it could go to any one of the angles, honestly. They just chose A. Next, grab your protractor. You want to line it up so the center is at P, and then use that to draw a 120 degree angle to segment PA. Just like you see right there, nice and pretty. Then you want to draw A prime at the end of that segment. So you have A prime. And those two segments will be the same length. Okay? That's important. So whatever length PA was, PA prime needs to be the same length. Then repeat those steps for the two vertices. So you draw a segment to B. The protractor lines up and makes 120 degree angle. You put B prime. And again, you make sure the segment is the same length. If it's not the same length, you're wrong. And then you go to point C, do it again, put point C, make sure it's the same length. And then you can connect the dots on your new triangle, A prime, B prime, C prime. And that is your rotation. So you can rotate things, 130, 220, 310. You can go past 360 even. Now, you do have coordinate rules that you can use if your rotation is 90, 180, or 270 around the origin. So it has to be around the origin. That's kind of important. Otherwise, use your protractor to do the angles. So your rules, these are for counterclockwise. If you're rotating it 90 degrees counterclockwise, flip the coordinates and change it so you have negative BA instead of AB. So basically, it's negate the Y and flip. To do a 180, it's just change the sign on both of them. So negative A, negative B. For 270, you switch them again, but this time what was the X becomes negative. So if you had AB, now you have B, negative A. If you want to go clockwise, you just subtract the degree from 360. That's the same thing as a counterclockwise rotation. So if it says like 90 degrees clockwise, you'd go, well, 360 minus 90 is 270. So that's 270 counterclockwise. Oh, there's the rule for 270. B common negative A. So you're going to graph quadrilateral RSTU. Your vertices are R31, S51, T5, negative 3, and U2, negative 1, and its image after a 270 rotation about the origin. So what you want to do is use your coordinate rule to find the new coordinates. It's just easier to do that first. Remember, so 270 rotation, the rule is you go from AB to B comma negative A. Or in other words, change the sign of the X and then flip the two numbers. So if I'm at 3, 1, now I'm at 1, negative 3. 5, 1, 1, negative 5. 5, negative 3 is negative 3, negative 5. And 2, negative 1 is negative 1, negative 2. And you just go in there and start graphing everything. So there's R, S, T, and U. It's going to rotate around the origin counterclockwise. And look just like that. So again, you have your postulate here that a rotation is a rigid motion. Again, rigid motion means that all the line segments are the same length, all the angles the same measurement, nothing gets changed. So you already had this for translations and reflections, now you have it for rotations also. So compositions, like we did before, you're going to do multiple transformations here. So if you have segment RS has R negative 1, negative 3, and S is negative 2, negative 6, you're going to reflect it in the Y and then rotate it 90 degrees clockwise about the origin. So first you're going to graph RS. So there's your R, there's your S. Reflect it in the Y-axis. That's an easy one. So R is 1 space left, so now it is 1 space right. S was 2 spaces left, now it's 2 spaces right. There's your coordinates. You want to use your coordinates because of the rotation rules. So that's a 90 degrees clockwise. You saw the green line there moving. So that is 360 minus 90 is 270 counterclockwise. So use that rule, which we just did. So it's A comma B becomes B comma negative A. So if R prime is 1, negative 3, now R double prime is negative 3, negative 1. And if S prime is 2, negative 6, S double prime is negative 6, negative 2. Like that. Now, to write a coordinate rule of decomposition, so your first transformation would be AB arrow negative AB. Your second transformation was the clockwise rotation, or 270. So now negative AB became B negative negative A, which gave you BA. So your coordinate rule would be A comma B arrow B comma A. So now you can use compositions to rotate your figures when your center of rotation is actually on the figure. Because so far it's been around the origin or some other location. So now it's going to be a point on the figure. So what you're going to do is you take your figure, you're going to translate it so that the center of rotation is on the origin. Then use a rule to rotate it, move it back to where it was. It looks like this. So triangle ABC has vertices A, 1, 2, B, 2, 4, and C, 3, 3. And you want to do a 180 rotation about point A. So your rule, translate the figure until your point of rotation, which is point A, touches the origin. So if it had said around point B, we would move it until point B is on the origin. If it had said around point C, we move it to point C is the origin. But it said around point A. So we're going to translate that until A is touching the origin, just like that. And you write your rule for that, and that's translation rule. So it was A minus 1 and B minus 2, or X minus 1, Y minus 2. But they're using A's and B's here. So if you were at 1, comma 2, A prime is now at 0, comma 0. So B, 2, 4 has to follow the same rule, A minus 1, B minus 2. So B prime is at 1, comma 2. And then point C has to follow the same rule. So if it's at 3, 3, now you have 3 minus 1 and 3 minus 2. So C prime is at 2, comma 1. Which you knew that by looking at the graph there, you knew that. But you're not using graph paper. If you're using regular paper, you want to have this stuff down too. So now, use your coordinate rule for 180 around the origin. So you want to spin it like that, basically. The rule is negative A, comma negative B. So just change both signs. So A prime is at 0, 0, and it would stay at 0, 0. B prime was at 1, 2, so now B double prime is negative 1, negative 2. And C prime is at 2, 1, so now it's negative 2, negative 1. So now you get to translate it back until A double prime are touching A. Just like that. So that was plus 1, plus 2. So A triple prime is back at 1, comma 2. B double prime is at 0, 0 now. And C double prime is at negative 1, 1. Okay, rotational symmetry. This just means that I can spin the figure 180 degrees or less and get it to match up around itself. So some of the figure is called the center of symmetry, and you can rotate clockwise or counterclockwise. So if you cannot get it back onto itself under 180, then it doesn't have rotational symmetry. Now, if a figure has rotational symmetry, its order of rotational symmetry is how many times you can map it onto itself in one full rotation around it. So we decide if it has rotational symmetry or not, and if it does, the order. So regular hexagon, which is back on the right-hand side there. I can spin it, and it's already on itself. That's at 60 degrees. So if you take 360 divided by 60, you get 6. So that means there are 6 rotations that could map the hexagon onto itself. So your order of rotational symmetry is 6. The trapezoid does not go back onto itself. So 180 or less, it does not map it back onto itself. So it does not have rotational symmetry.